Okay, so what I'm going to talk about is something which has been coming up a lot recently. Of course, we're worried about climate change, and one question is whether or not plasticity would help or hinder that response to climate change. So when we think about climate change, this is often our response. Oh no, horrible things are going to happen, everything's going to go extinct. But then people have said, phenotypic plasticity, everything will solve all our problems. But is that true? So, in order to address this question, what we did was a computer simulation model looking at an evolutionary scenario where we contrasted evolution with and without plasticity to see what would happen. So, the model was an individual-based model in which, so you have individuals, it's hard selection, individuals are producing offspring. The scenario is just a simple continuous directional change in the mean environment. So that's the simplest kind of pattern of change you can imagine. And in this case, we set it up so that the rate of change is going to be greater than mutational variation is able to respond. So, so if you have no plasticity, as you'll see, you're going to go extinct. And so, will plasticity itself evolve quickly enough to compensate for that change, and what might restrict that? So, here's a little bit about the model. So an individual consists of two classes of genes. Genes which are not plastic, that is, their expression does not depend upon the environment. And then another set of genes in which the expression is dependent upon that E, the environmental state. So there's 10 or 5 diploid loci for each of those types. And then there's that term B, which affects the magnitude of the expression. You can think of it in a sense of how much we're allowing plastic variation to be expressed relative to non-plastic variation. We start by, there's genetic variation for both non-plastic and plastic alleles, but the mean expression of those plastic alleles is 0 in the initial environment. That is, there's underlying genetic variation for plasticity, but it's not being expressed in the initial environment. But in addition, what we add for some of the scenarios is a cost to plasticity, in which that cost is proportional to the sum of the square of the value of the alleles. In other words, the mean expression of the alleles might be 0, but there's still going to be a cost. You could think of this as a cost for, let's say, maintaining the underlying machinery for plasticity separate from its phenotypic expression. There's lots of different kinds of costs of plasticity. This is sort of an intermediate version, and the overall patterns probably aren't going to differ depending upon exactly how you express that cost, although the details would matter. But the point is that the cost is going to increase as plasticity evolves. That is, as you get more and more plastic, the cost goes up, and it's independent of the phenotypic expression. So, first of all, let's start out with the simplest, with the case where there's no cost of plasticity. So I'll go through that scenario first. And first we're going to look at survivorship. So the things are, the environment's changing. There's a demography that's going on for about the first 20 generations. Given the rate of change we've got going on here, everything is fine, at which point then the optimal phenotype has been moving far enough away from the starting conditions that some of the populations begin to go extinct. So this is the probability of survival over that first 100 generations. Remember this B term, this is the amount, basically the expression of plasticity. So small values of B mean less plasticity, large values of B mean more plasticity is being expressed, and not too surprising, the more plasticity you can express, the more likely you are to survive because you're able to keep up with that environmental change. So that's not too surprising. So plasticity helps you survive. Again, over that same 100 generations, here's what's happening to plasticity itself. So plasticity here is relative to the optimal. So if the population is at relative plasticity of 1, it means that it's exactly matching the optimal phenotype through plasticity alone, without any help from those non-plastic alleles. And again, the more plasticity being expressed, the faster plasticity evolves, the closer to that optimum you get over that first 100 generations. Now we let the thing run for 1,000 generations, and so here's what's happening at 1,000 generations. Now, the x-axis here is not time anymore, but the rate of change. So we looked at what happened at various different rates of change. So change, rate small, rate large. The stars here, this is the population where B equals 0, i.e. there's no plasticity at all, and as you can see, populations go extinct at a fairly low rate of change. The survival to 1,000 generations increases as the amount of plasticity increases. Again, what you would expect. And here's what's happening with relative plasticity. So even those populations that have relatively low plasticity out at 1,000 generations, they have evolved to almost pure plasticity. So with no cost to plasticity in the system, all is very good. So the last little bit here is phenotypic lag. This is in standard deviation units, how far behind the optimum the population is tracking that optimum. And with plasticity, you're not quite at the optimum the whole time, but you're pretty close. And it doesn't really matter how fast the population is evolving, which makes sense, right? Because we're at almost relative plasticity of 1. So at that point, the populations are keeping up with this change because of plasticity, and as you can see, no plasticity. There's lots of lag, and then you just go extinct. So these are for the populations that survive that 1,000 generations. Okay, so if there's no cost of plasticity, everything's fine. Populations will keep up with environmental change. But what happens when we add a cost of plasticity? So here's the graph I showed you a few minutes ago about survivorship as a function of change when there's no cost. Here's where there's a cost. And notice the difference in scale here. Right, so the stars is actually the same stars. So with a cost of plasticity, the survival goes way down, right, for equivalent amounts of rates of change. So in fact, we had to shift the entire rate of change that we were looking at when we have a cost. So with a cost, you greatly decrease the survivorship. Now let's look a little bit closer at this survivorship because something very interesting is going on. Here's these stars, right? That's with no plasticity at all. So that's the base rate if you just have non-plastic response. Everything at this rate of change, everything goes extinct. Notice at low amounts of plasticity, survivorship is actually lower than it is with no plasticity at all. And it's only once you have relatively high rates of plasticity that you actually do better than not being plastic. And the reason is quite simple. What you have in this case is there's a cost to this plasticity that doesn't actually give you enough benefit, right? So the cost of plasticity is outweighing the benefits of that plasticity. So unless the plasticity is relatively large, you're actually better off not being plastic at all. So a couple of other things. This is the lag, how far behind that optimum you are. And as you can see, even with plasticity, even with relatively high rates of plasticity, the lag can be substantial. This is standard deviation units. So you lag behind the optimum. And in terms of the amount of relative plasticity, again, even with relatively high plasticity, you're not anywhere close to 1. That is, it's actually a lot of the non-plastic alleles that are responsible for you keeping up with that environmental change. So when there's a cost of plasticity, it really doesn't help a whole lot. So plasticity can increase survivorship in the face of climatic change. However, but only if the plasticity is not costly. If plasticity is costly, then survivorship and that evolutionary response can actually be much lower than when there's no plasticity at all. And so a little bit of costly plasticity can be worse than no plasticity. Now, the one possible saving grace here is that so far, when people look for cost of plasticity in eukaryotes, there's very little evidence for that cost, so that may be a saving grace. But clearly, if we're concerned about this, that's something that we're going to need to measure. And in terms of the future, we're going to go with this. And this was with the simplest sort of change, right? A simple directional change through time. Obviously, much more complex patterns, as we've seen in some of the talks this morning, are much more realistic, where there's variability around that mean drift, and that may change this trade-off between cost and benefit of plasticity. So, with that, are there questions? Yes.
What are some ecological examples to cost plasticity, and how would you go about measuring those?
So you can measure cost of plasticity by regressing fitness against the magnitude of plasticity. There's a standard statistical procedure for doing that. And as I say, where people look for it, there's a couple studies have found some evidence of cost, but for the most part, they haven't found it.
Yeah, you model the cost of plasticity as not being related to expression.
Yes.
So you have a cost even if you're not expressing any of your plastic alleles.
Yeah.
Are the results, do you know if they're at all sensitive to changing where you put the cost?
The same overall pattern is going to occur. So in other words, you might shift that where that survivorship curve is going to be, but the overall pattern would still hold. So what we modeled would be the equivalent of the cost for maintaining the machinery to be plastic, for example.
But on that, I suppose, what about if you varied the cost of plasticity relative to the magnitude of the expression?
Again, that would change the details of where things are, but the qualitative pattern should remain the same.
So